Okay, so for the questions of this chapter, there are some that are related to symmetries, and specifically they're related to Newton's theorem. So I thought that those problems are probably a little bit difficult for you to do without any other background. So I'm recording a few additional lectures just on Newton's theorem. So look out for those and watch those before you start trying to tackle those problems. The next thing, I've asked you to calculate the time dependence of some observable that depends on t, x, and p. Well, this is very similar to the kinds of things that we were doing. So if you calculate d by dt, we will clearly have a term which is d omega dx times by x dot. We had that before. We'll have a term that looks like d omega dp times by p dot. And the only difference to what we had before is that we must now include a term that looks like d omega dt. It's useful, or it's good to think about functions that also have an explicit dependence on t, because this is the most general situation you could think of. If you can deal with the time dependence of an observable like this, then you can deal with the time dependence of anything. Okay, so that's the first thing. Now, here's the second thing. Before I said that if you've got a symmetry, then under the symmetry, I said that your action should be unchanged. So the S should go into S prime, which is equal to S. And in one of the problems in the for this chapter, I've pointed out that it's good enough if S prime is equal to S plus a constant. And what I mean by this constant, I mean independent of which solution you choose to evaluate things on. So let's just try to see why it's good enough if the action changes by a constant. Well, let's imagine here I've got the action. And let's imagine on this axis, okay, a bit hard to draw, but I'm going to say I'm plotting the solutions. Okay, so I'll just call it solutions. And what the action looks like, maybe it's a function that looks like this. Now, the thing that's important is not the value of the function, but the thing that's important is where the action is minimized, because that tells me which is the solution to the classical equations of motion. You know, the classical solution minimizes the action. Now, if I was to add a constant to S, well, then this whole curve gets shifted down or up. So each point is just shifted by a constant, but in particular, the minimum of the action is not changed. So whatever minimized the black action will also minimize the blue action. And as far as we're concerned, we're just using the action to tell us something about the classical solutions. The classical solution is the solution that minimizes the action. And it's because of that the action or the action plus a constant are equally good for our purposes. Great. So those were the only hints that I really wanted to give you. The problems for this chapter are a little bit challenging, so think hard and good luck. You do most of your learning by solving problems. So solve the problems as well as you can, and let's get cracking with the next chapter.